Okay, hello everyone. This is section 8.1, matrices and systems of equations. If you haven't downloaded the notes, please do so. They are in Moodle. Or you can just keep pausing the video and write everything down, or write everything down first. It's up to you, however you want to do it. But we're going to be doing matrices and systems of equations. So we're going to be simplifying our life from sort of the longhand version of Gaussian elimination that we just got done doing. And also, I decided not to do a quiz. I'm going to give you a take-home quiz on Friday, so you don't have to worry about doing a quiz on Monday. Just make sure you watch the video, and you'll see. Just make sure you watch through this video because we're going to pick up from where this video leaves off on Wednesday. Okay? And anything else? Okay. Okay, so in this section, you're going to study a technique for solving systems of linear equations. Oh, also, too, we're only going up to the first 17 pages. I don't know if I already said that for this video. So this technique involves the use of a rectangular array of real numbers that we call a matrix. So, and the plural of matrix is matrices. Okay. So this definition, I know may look, you see all the symbols, but really if you have m and n are positive integers, then an m by n, so we read that m by n, not m times n when we're talking about matrices, we say m by n. Matrix is a rectangular array where horizontally we call the rows are horizontal, the columns are vertical. And each entry, what we call A sub ij of a matrix, is a number. And an m by n matrix has m rows and n columns. And we usually denote matrices by capital letters. Okay? All right. So if m is equal to n, this is page 4. Wait, hold on. Wait, hold up. I want to make sure I go in the right order. And I forgot to write in, so it's matrices if it's plural. Okay, and so the entry in the ith row and jth column is denoted by the double subscript called aij or a sub ij. Okay, and so for instance, a sub 2 3 refers to the entry in the second row and third column. And so for instance, if we had the matrix, the 3 by 3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and matrices in mathematics, the same notation is sometimes used to mean different things, and the way you can tell which notation is going with what is through the context. So if I'm seeing brackets in this section, then I know you're talking about matrices. Okay, so just keep that in mind. So this is a 3 by 3 matrix. And if we wanted to find the value in the A23, or A sub 2 3, then that would be the second row. So we're looking in the second row, third column. And so A23 would equal 6. Okay, so I hope that makes sense. And a matrix that has only one row is called a row matrix. And a matrix that has only one column is called, you guessed it, a column matrix. I'm sorry, these lines are still not long enough. And a matrix having m rows and n columns is said to be of order m times n, or m by n. And so this example here, that's a 3 by 3 matrix. And so the order is 3 by 3. If we had something like 1, 2, 3, 7, 1, 4, let's add an extra column. So this would have order, what do you think it would have? 2, 3, correct. 2 by 3. This would be order 2 by 3. Okay. If m is equal to n, then the matrix is, we call it square. Okay. And it looks, because it looks square, right? Because if, for example, a 2 by 2 matrix, 1, 1, 0, 0. It's square, right? 3 by 3, 4 by 4. Okay, so if it have order m by n, m by m, or n by n, and for a square matrix, the entries along the entries A1, A sub A11, A22, A33 are the main diagonals or diagonal entries. All right, so I'll do another one. So 1, 2, 3. If we look back at 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, here at this 2 by 2, those are the main diagonals, and those are the main diagonal entries. Okay. All right. So looking at this, and you're actually, I think, in your notes given the solution, but I would just want to make sure you understand the order of each matrix. So looking at A, it's just one row and one column, right? So this is what? A 1 by 1 matrix. Okay. B has one row, how many columns? 4. So this is a 1 by 4 matrix. C has 2 columns, 2 rows, 2 columns, so 2 by 2. And then D has 3 rows, 2 columns. So this is a 3 by 2. And those are the orders. Okay, a matrix derived from a system of linear equations, each written in standard form, with the constant term on the right is the augmented matrix. And when we look at an example, this will make more sense. Hopefully, it will. Moreover, the matrix derived from just the coefficients of the system, not including the constant terms, we call that the coefficient matrix of the system. Okay. All right, so let's look at this system right here. So you're given, this is the systems of equations. We have 3 equations, 3 unknowns. And so the augmented matrix is on the left-hand side. You see those represent the coefficients of each of the 3 equations. And on the right-hand side, that represents the constants, right? On the right-hand side of the equal sign. And we call this an augmented matrix. Okay. But if we just looked at the left-hand side, which if we're just looking at the coefficients of each of the equations, then that's a coefficient matrix. Okay, so you have an augmented matrix and a coefficient matrix. Okay. Also note that we use zeros for the coefficients of the missing variables in the third equation. So in this third equation here, there was no y, so we use 0. Okay. And also note the fourth column of constant terms in the augmented matrix. Okay. And so when you're forming either the coefficient matrix or the augmented matrix of a system, you should begin by vertically aligning the variables in the equations and using zeros for the coefficients of the missing variables. Okay, so I actually want you, just for practice, to write the coefficient matrix and the augmented matrix for this system here. I just created it, so this isn't in your notes that you printed off. So write the augmented matrix and the coefficient matrix of this system, and if you do it correctly, you can get an extra credit point on this last exam that you guys just took. All right, so I want you to practice, find the augmented and the coefficient matrix, and I'll collect this at the big. Like I said, there won't be a quiz on Moodle. It's going to be a take-home quiz on Friday, but this right here is due at the beginning of the class on Wednesday. Okay. Okay. So now we're still going to use. Remember, we talked about our elementary row operations, and we've studied this already with the Gaussian elimination, what we just did, and so we can use these properties in terms of our matrices. And so just recall that we can interchange in 2 equations, multiply an equation by a non-zero constant, and add a multiple of an equation to another equation. And so in matrix terminologies, these 3 operations correspond to elementary row operations. So elementary row operations. I'm sorry, it's not enough room on these lines. I'm gonna have to do something about that. Okay, so an elementary row operation on an augmented matrix of a given system of linear equations produces a new augmented matrix corresponding to a new but equivalent system of linear equations. So this is really what we've been doing. Now we're going to use we're using mathematical symbols and matrices to simplify our lives, okay? And so two matrices are what we call row equivalent when one can be obtained from the other by a sequence of elementary row operations. And so the elementary row operations are as follows, and here's the notation. So we're going to start using this notation, shorthand notation, and it varies a little, so I'm going to go over it with you. But the notation, if you're interchanging any two rows, that's sort of biconditional arrow, but it's actually going to be curved. I'll show you in a minute when we look at a matrix. Then we can multiply a row by a non-zero constant, and then we can add a multiple of a row to another row. Okay, and so we've done this before. It's now looking at in terms of matrices. Okay, so we're going to interchange. So here's the original matrix here, and we're going to interchange the first and second rows. Okay, and you know how we would say interchange row 1 and row 2, or how we would write it in words. Now we just can use symbols. And where you write it, so be very careful, and I'm going to go back over this in class, but this matrix here is our new matrix, and this tells us what happened to the previous matrix. Okay, so this is already done, so the switching is already done. Okay, this is just what happened in this is saying what's happened in the previous matrix. I'm sorry. All right, so we switched row 1 with row 2. So that's what that symbol means, to switch row 1 with row 2. Okay, this example here, so I'm showing you different matrices with the different row operations. Of course, we're going to be doing the row operations together with similar matrices with one matrix. But I'm just showing you how to use this. So this is, if the original matrix is here, then let's say we wanted to multiply the first row of the original matrix by 1/2, right? Because we can do that. That's one of our elementary row operations. Okay, and so this is the final product of this. So again, 1/2 times row 1. And this is where students get confused, because they're thinking, oh, I need to multiply it again. You don't need to multiply by half. When you put that row operation in your matrix, this notation, this is telling me the matrix. If I look at the matrix before this matrix, then you took 1/2 of row 1. Okay, so if I look back at this matrix, if I look back at row 1 of this matrix, I multiplied that by 1/2, and this was the result. Okay, I hope that makes sense. And then add -2 times, so that's the third elementary row operation that you can multiply it by, add a multiple to one row and add it to another. Okay, and hold on. Okay, so we're adding -2 times the first row to the original matrix to the third row, and so this is the final product of that process. Okay, so what we did here, and this is why it's condensed. And so note that the elementary row operation is written beside the row that is changed, not the row before it. And so I hope you understand the difference. So you don't write this operation for that row, you write it for the final row that's been changed. So this is telling me, if I look at the matrix before this one, that you took -2 times the first row and then added it to the third row, and this was your final product. I'm going to stop this video here because it's going over 15 minutes almost.